Welcome to Math TV with Professor V. In this video, we're going to look at examples of how to find volumes using double integrals. If you haven't already watched the lecture video outlining the concepts behind setting up double integrals over general regions, I'll link it here because that gives you all the foundational information that you need to complete these exercises. The purpose of this video is just to work through extra examples to help you all as you're completing your homework assignments. So when we're looking at a volume for a solid and we're going to compute it using a double integral, remember we use the following general setup. So the volume is equal to the double integral over d of f of x, y, dA. And I'm briefly going to explain what everything represents. So d is the base of your solid. You could think of it that way. It's the region that you're going to integrate over. So think of it like that's your base of your solid. And then f of x, y, we know that we can say z is equal to f of x, y, right? So that's giving you the height of the solid. And so notice here the graph that's shown, we have the base in the xy plane. It's going to be a general region, not just some plain old rectangle. And then the function, that's going to also have to be given to you. Typically we work with the function of x and y, so we can isolate z. And then that will give you the height of the solid. And then here is your three-dimensional solid whose volume we're going to compute, okay, with this integral. Now, when you're setting up your double integral over the region D, you have a few options if you want to set up the order of integration dy dx or dx dy. Remember, that's what dA represents. So this can be either dx dy or dy dx. Which order you set up really depends on the region. So we're going to graph the region, the integration region for every single exercise, okay? And this is really important. Don't wait for the textbook or your teacher to tell you, oh, graph the region D. You got to do that anyways, okay? Time to take some accountability as a math student. So let's go look at some setups. And I have 3 exercises picked out for you guys. First one, find the volume of the given solid using a double integral under the plane 3x plus 2y minus z equals 0, and above the region enclosed by the parabolas y equals x squared and x equals y squared. So these two parabolas are going to enclose a region, and that region is D, over which we're going to integrate, okay? So let's start off by figuring out the intersection and what D looks like. And I'm just going to graph D in the XY plane. I don't need a 3D graph to set up and compute this volume. So let's go ahead, find the intersection. Okay, y is equal to x squared and x is equal to y squared. So that means y is equal to y squared. Yes? Good. Love it. So this means that y squared minus y is equal to 0. So we have, if we factor y times y minus 1 is 0. So either y equals 0 or y equals 1. And if y is 0, then x is 0. And if y is 1, then x is 1 also. All right. And let's go ahead and graph this little region here. It's going to be predominantly, in the first quadrant, the region that's enclosed by these two parabolas. So here's x, here's y. All the action happens at 0, 0, and 1, 1. So here we go. Here's 0, 0. Here's 1, 1. And y equals x squared is going to be below x equals y squared, which is right here. So let me label each of them. This is x equals y squared. This is y equals x squared. And then here is the region D, okay? All right, now when you set up your double integral, the limits are dependent on the region D. So you have to decide, okay, are you treating it as a type 1 or type 2 region. I'm not going to really say type 1, type 2 because it's dependent on the textbook, but that's what most of them refer to it as. So here's the idea. When you set up your double integral, one of the limits is going to have to be for x, the other set of limits has to be for y, and then you have your function of x and y. If I set it up this way where x is the outermost integral, then I have to integrate with respect to x last, yes? So then we would have dy dx. Or you could have a double integral if the outer integral represents the limits for y. These have to be constant, outside ones have to be constant. If this one represents the limits for the region in terms of x, then you would have f of xy and it would switch. It would be dx dy. So watch what's going on. Dx would match with the inner integral. Those have to be limits in the x direction, horizontal, okay? And then here we have dy on the outside, and then that would have to match up here with our limits for y, and those need to be constant. The outermost limits have to be constant, otherwise you won't get a number for your answer. Dx, these are limits for y, dy, okay? So you have to decide which setup is easier, okay, for the problem. In this case, both are equally easy, so I'm gonna set up both for you. Check that out. When you have limits for x, let's look at this first case. Limits for x on the outside, these ones are gonna be the constants. And then when you're setting up the inner integral, limits for y, you want to see, is there a function that bounds d above and below? So look here. Say, for example, we're going to use this first setup where we're going to integrate dy and then dx. If I have limits for x, and those are going to be my constant limits, this is setup 1. And those are my constant limits. Look at the x direction. Okay, region D lives between 0 and 1. Yes? 0 and 1. So those are going to be my limits for x. No problem. Now, on the inner integral, the limits need to be for y values. Is there a function bounding the region above and below? Why, yes. Look, this is the lower bound. This is the upper bound of the region. It goes this way. You always have to go increasing direction. Okay, wherever you start, that's going to be the lower limit for the integral. That is y equals x squared. Okay, x squared. Now, what about the upper limit? This needs to be given, this upper limit, in terms of x, right? So we have x equals y squared. That means y is equal to plus or minus rad x. Since we're in quadrant 1, I'm just going to use positive rad x. So that goes up here. Very nice. Now, what is f of xy? Remember, that gives me the height of the solid, and the height is being determined by the plane here. All right, so I need to rearrange the equation of the plane. So I have a function of x and y. It's pretty easy. Just move the z over. So we have z equals 3x plus 2y. So that is my f of xy. All right, looks good. So now I'm going to fill that in here. F of xy was 3x plus 2y. And then we have, check your integration order, dy dx. Before I keep going, look at, you have to make sure everything's under control. We're integrating with respect to y first. Yes, these limits are bounding the region D in the y direction. Notice they are y defined in terms of x, which is perfect because the next variable I'm integrating with respect to is x. So this variable has to be the same, and then these are constant limits for x, constants on the outside. Okay, love it. Now let's go ahead and integrate. Let me add a page because we were just having so much fun. That took up more space than I thought. Okay, so remember when you're doing an iterated integral, you treat, it's basically partial integration, right? You hold one variable constant at a time. So first I'm going to integrate with respect to y. That means I'm treating x as a constant, all right? Rewrite everything each step of the way. Don't be sloppy. So we've got 0 to 1. All right, I'm treating x as a constant. So if I integrate with respect to y, that's just going to become 3xy plus, And then antiderivative of 2y would be y squared, right? Because we're going to divide by the 2. And then this all gets evaluated from x squared to rad x, and then I still have dx out here. Very good. Now, you're going to have to remind yourself, be careful. I just integrated with respect to y, so these limits of integration I plug in for y. Keep reminding yourself because it can get confusing. Plugging them in for y, so we have integral 0 to 1. 3x times, if I plug in rad x for y, that's 3x rad x, that's 3x to the 3 halves, plus y squared, if I'm substituting in rad x for y, and then I square it, now it's just plain old x, minus, now I substitute in x squared for y here, so that's going to be 3x cubed, minus, and then again, x squared gets substituted in for y. If I square it again, now it's x to the 4th. Close up your parentheses, dx. Okay, the worst is over. Now you should feel like you got in a time machine and you're back in Calculus 1 class doing these sweet little integrals. Antiderivative of 3x to the 3 halves. Add 1 to the exponent, so it's going to be x to the 5 halves. Divide by the new exponent, so you're multiplying by 2 over 5. 3 times 2 over 5 is 6 over 5. Plus antiderivative of x, 1/2 x squared. Minus, this is going to be 3 over 4 x to the 4th. Minus 1/5 x to the 5th. And we evaluate this from 0 to 1. What lovely limits of integration. Aren't you grateful? So we've got, plugging in 1 now for x, 6 over 5 plus 1/2 minus 3/4 minus 1/5. That's the upper limit. Minus, if I plug in 0, everything's 0. Just always check. Every now and then there's like a cosine of x or e to the x that'll throw you for a loop. So don't forget to at least check that all the terms are 0 when you plug in 0. And what do we get from here? Resist the urge to grab your calculator. Have some self-respect. So this is 6/5 minus 1/5. Come on, guys, that's 1. And then 1 plus 1/2, that's 3 halves. 3 halves minus 3/4 is just 3/4. Look at that. We don't even need a calculator. Very good. Now, I also told you we could set up the integral using the other order of integration for this region as well. It was equally easy. Let's go back and look at y, okay? So if we were to set up the region where we integrate with respect to x and then y second, remember those outer limits for y have to be constant. So I'm going to erase these little arrows here because we're going to do things a smidge differently, okay? Don't panic. So now look here. Say we're going to use setup 2. Limits for y need to be constant. Well, look, y also ranges from 0 to 1. Yes? That's where the region D lives. Those are constant limits. Okay, love it. Now we're going to use the inner integral to represent limits for x. So when you're setting up limits for the region in the x direction, you have to set up the lower limit as whatever function is the boundary for the region on the left. That's the lower limit. And then the upper limit would be the boundary for the region on the right. To help you, you can draw horizontal lines in the x direction just like we did for the first setup in the vertical direction. So go this way. See this? Okay, it always has to go in the increasing direction. So you would always go from left to right, smaller to bigger. So whatever function here, look, bounds the region on the left, that's going to be the lower limit of our integral. And then this time, remember, we have to give x in terms of y, as a function of y. So I'm going to use y squared as the lower limit, since that's bounding the region on the left. And then the upper limit, what's bounding the region on the right? It's x squared equals y, but that means I'm going to use x equals rad y. Positive because we're in quadrant 1. So this is rad y. Do you see the difference? And then not much else changes. F of xy, you're just going to use the same thing, 3x plus 2y dx dy. All right, and then I'll let you work through the rest of the integral. The process is pretty similar. And guess what? You end up with 3/4, as we should. Otherwise, something went awry. Okay? Now, not every region D will be easily set up with both orders of integration. So sometimes one is preferred, and just be ready to follow the directions, because sometimes, you know, the textbook might ask you to set up both or one or the other. Good. All right, let's move on. Next example. Again, we're finding the volume using a double integral that's enclosed by the cylinders z equals x squared, y equals x squared, and the planes z equals 0 and y equals 4. Okay, so remember when we use the word cylinder, we're not actually talking about what you typically view as like a cylindrical solid, right? A can shape. We're just talking about a cylindrical surface when you have a graph in 3 space, but it only involves 2 variables at a time. All right. So let's graph it. Z equals x squared. Just graph z equals x squared in the xz plane and then project it parallel to the y-axis. You should have practice doing this. So z equals x squared. I'm not going to like stress about making it perfect. I'm just going to draw roughly. Here's a parabola in the xz plane. Okay. And then I'm going to project it parallel to the y-axis. All right. So how am I going to do that? You draw a little line segment parallel. Ooh, I don't like that one. Parallel to your y-axis. And then I'm just going to attach it to various places. Here. Ooh. Let's make it more precise. That's better. Copy, paste. Now we're in business. Paste it a few times, so you just add some dimension. Or you bust out your ruler and you just draw a bunch of little segments, right? Do one more down here. Okay, these can go. And then now I'm just gonna connect. Lovely. So this is z equals x squared. This is gonna give us the height of the solid. How do I know that? Because right now we're setting all of them up with the height being given by z. But also you can see from the setup and the rest of the problem, it's going to work that way. Then we have y equals x squared. Okay, so I'm going to draw a parabola in the xy plane. It's like this. And then what happens is, to not make the picture too messy, so this is going to be projected parallel, right, to the z-axis. And these are going to intersect. So the solid is going to live underneath the cylinder, z equals x squared. That's going to bound it above. That's going to give the height of the solid. And then the base region D that lives in the xy plane is also bounded. Notice here by z equals 0, so that's just the xy plane itself. And then y equals 4. So basically we're cutting this off right here at 4. And the entire solid is just going to live above this region. Well, what is that region bounded by? It's bounded by y equals x squared and y equals 4. That's my region D. So let's graph that just in the xy plane. Notice how much graphing I'm doing, and the directions did not say graph. That's what you need to do to be successful, okay? If you think you're going to set these up and not graph, you're just kidding yourself. Don't even talk to me. It upsets me when students try to just solve them and not graph. Okay. So the parabola y equals x squared is bounding the region. I know it's going to intersect y equals 4 at 2 and -2. That should be obvious to us all by now. And I'll throw a couple more points on for good measure. Why not? Okay. So here is the region D. Lovely. Now let's decide. Oh, let me color code it the same way so you know where it went, right? So it matches the 3D graph. Let's decide. Is it easier to bound this region above and below or on the right and the left? Okay, I say above and below. Here's why. Bounding the region above is y equals 4. Bounding it below is y equals x squared. And that's consistent, right? Throughout the whole region. Like if I were to draw those little line segments moving up, it's always y equals x squared on the bottom, y equals 4 on the top. If you were to try to do it the other way, what bounds the region on the right? Well, it's y equals x squared, but I would have to give it as x equals rad y. And then what bounds it on the left? It would be x equals negative rad y. I don't love it as much, right? I mean, it's just going to be a little messier to deal with. Up to you. You can try it. All right, try it. But I say it's easier to set it up the other way. So that means if we're bounding the region above and below, these are going to be the limits on the inner integral. They're limits for y. So the outer integral's limits have to represent the bounds on x. So that's going to be from -2 to 2. All right, so here we go. So the volume is going to be the integral. X's limits go from -2 to 2. Y's limits go from x squared to 4. Do we all see it? Good. So -2 to 2, those are limits for x. Limits for y, x squared to 4. It has to match visually. Look, this is the lower limit. This is what bounds the region below. This is the upper limit. This is what bounds the region above. Then we have f of x, y. Remember, what's determining the height of the solid? Z equals x squared. And then we set up the order dy dx. Notice everything's matchy-matchy. These are limits for x. They're constant. Here's dx. These are limits for y. And they have to be in terms of the variable that you're going to integrate with respect to after. You better not have any y's in there. Good. Here we go. So we have -2 to 2. Antiderivative of x squared with respect to y. So I'm just treating x like a constant, as if it was a 5. That means it's just going to be x squared y evaluated from x squared to 4 dx. All right, then I'm going to substitute these limits of integration in for which variable? Always remind yourself, who did I just integrate with respect to? Y. So they get substituted in for y. All right, so we have integral -2 to 2, 4x squared minus x squared times x squared, that's x to the 4th, dx. All right, we're home free. Do a little celebratory dance. So we have here antiderivative of 4x squared, that's going to be 4/3 x cubed minus 1/5 x to the 5th. This is from -2 to 2. And then substituting in our limits, we have 4/3 times 8, so that's 32/3, minus 2 to the 5th, again, 32 over 5, that's the upper limit, minus, and then if I plug in -2 now, I have a -32/3 minus, but then that's going to become positive, won't it? It certainly will, 32/5. Okay, and we end up with 128 over 15. Now, you might have noticed that the solid is symmetric with respect to the y-axis, and our integration region D is also symmetric with respect to the y-axis. So if you wanted, in terms of setup, to make things a little bit easier, you could have just doubled the entire integral and then gone from 0 to 2 x squared to 4 x squared dy dx. That way you have a lower limit of 0. But you have to be really careful because d has to be symmetric with respect to the y-axis when you do this, and so does z, what's giving you the height. Otherwise, doubling it won't make sense. You won't really have, two equal halves over the y-axis. All right, how are we doing so far? I have one more for you. And here we go. So find the volume of the solid that's bounded by the cylinder. X squared plus y squared equals 1. This time it actually will look like a cylinder. And the planes y equals z, x equals 0, z equals 0, and we're only in the first octant. All right, here we go. Let's graph. Before I can graph the region D, I do need to graph this cylinder to see what is going on. So when you have x squared plus y squared equals 1 and z is missing, that means you're going to draw the circle, x squared plus y squared equals 1, in the xy plane, and then project it parallel to the z-axis. So here's 1, here's 1. I have this unit circle in the xy plane. And then let's project it parallel to the z-axis. So here's a couple little segments. Whatever variable is missing, you just project parallel to that axis. Make sense? Good. Do however many till you feel good about it. Okay. Do we feel good? Do we want any more? I think that looks nice. Here's our cylinder. Okay, maybe I should have done a few more. I don't love it. Yeah, that'll be good. Okay, so we've got this cylinder. And then we have the plane y equals z. Okay, so this plane y equals z, just draw the line y equals z again in the yz plane, and then ask yourself, which variable is missing? It's x. So you're going to project that parallel to the x-axis. Let me draw a little segment parallel to the x-axis. Copy. Paste it here. Okay, and you could just paste it right on top there. So here's the plane y equals z. So imagine it's cutting through the cylinder. All right, very good. That is actually going to determine the height of our solid. So the solid lives over this portion, right, of the circle in the xy plane and underneath that plane y equals z. So you can treat your f of xy as just equal to y, because remember, think of f of xy as z. So the plane is determining the height of the solid. X equals 0, z equals 0, that's just telling me we're staying in the first octant, okay? And so now let's figure out what the bounds should be for the region D. D is just that quarter of the unit circle in the xy plane. Okay, now you could switch to polar, but since this lesson comes typically in textbooks before you've learned how to do double integrals in polar, I won't do that, okay? But if you're comfortable, go ahead, switch to polar. So here, let me draw D. And we have to decide, do we want to bound it above and below or on the right and the left? And it really doesn't matter. It doesn't. I'll just do typically x on the outside, constant limits, y on the inside in terms of x. So since the equation for the circle is x squared plus y squared equals 1, that means y squared equals 1 minus x squared. And since we're in quadrant 1, I'm just going to use the positive radical. rad 1 minus x squared. That's bounding D above. And bounding D below is just y equals 0. Boom. And that's consistent throughout the region, okay? Good, so I think we're ready to roll. Limits for x are gonna go 0 to 1. Look here, 0 to 1 in the x direction. And then limits for y are gonna go 0 to rad 1 minus x squared. F of xy is just equal to y. So that's what we're gonna integrate. All right, so the volume is equal to integral 0 to 1, 0 to rad 1 minus x squared, y dy dx. Okay, antiderivative of y with respect to y, this is going to become 1/2 y squared. And then I'm going to evaluate it from 0 to rad 1 minus x squared, and then, dx. Just as a note, something I always tell my students, move your constants outside the integral so you can just get them out of the way, focus on the variables, not get overwhelmed. Okay, so right away, I want you to get in that habit. 1/2 integral 0 to 1. And then now these limits, I'm substituting them in for y. So rad 1 minus x squared, plug it in for y, you square it. Oh my goodness, I love it. Now it's just 1 minus x squared minus 0. Is this not the cutest integral you've seen all day? Okay. Antiderivative of 1 is x minus antiderivative of x squared, 1/3 x cubed. Evaluate this from 0 to 1. We've got 1/2 times 1 minus 1/3 minus 0. 1 minus 1/3 is 2/3. 2/3 times 1/2 gives us back 1/3. Ooh, love it. Okay. So that concludes the extra examples. Thank you for requesting this video. I'm sure lots of people also needed a little bit more explanation and exercises solved for them. I just wanted to show you guys something really quickly that I think helps a lot when you're understanding your integrals. When you have an integral from a to b, f of x dx, this typically represents, right, an area underneath the curve. And the way to tell is you have one integral sign and you're integrating a function. Each of those basically adds a dimension. So you have 1, 2 dimensions, area is 2d. If you have a double integral dA, this also will yield an area. Notice I have 1 integral, 2 integrals, but no function. That's why it's 2d. Now we're doing, I'll say it like this, d. Now we did a double integral over d. We had a function dA, and this was a volume, right? 3d. Well, count it up. It adds up. 1, 2, and this time we have a function, 3, hence 3d. And then guess what's coming your way? Triple integral over e dv. If you have no function there, 1, 2, 3. Again, that's going to give you a volume, 3d. Keep track of what your integral represents, right? Area versus volume, and then it can get more involved than that, but this so far should be what you're going to run into. Okay? Hope this video was helpful. Give it a thumbs up if it was. Feel free to share it with others. Subscribe if you haven't already, and I love taking requests. So if you have any other topics that you need or more examples from other videos, let me know. I'm happy to make them for you.